Welcome to Walkabout the Galaxy, the unflappable astronomy podcast, where the science is universal, the opinions are personal, and the episodes are quasi-episodic. We are Strange, Charm, and Top the Astroquarks, also known as Josh Caldwell,
Addie Dove,
and Jim Cooney.
Coming to you from the Walkabout. No, we're not at the Walkabout studio. We're on the internet again. Coming to you from scattered locations, distributed
to be fair,
around
we're
the
always on
Walkabout
the
studio.
internet to our listeners.
Yes, but when we're recording.
Yeah, I know.
We're near and dear to our hearts, the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. We're also at walkaboutthegalaxy.com. If you would like a Walkabout shirt and would like to support STEM education at the same time, send us an email at wtg@ucf.edu while we work out the kinks in our new Walkabout website.
Ooh.
Our stumper today is astrogeographical, and I was prompted for this by news about the Intrepid Voyager 1 and Voyager 2 deep space probes, which have been testing the boundaries of the solar system and also testing the boundaries of just how long a frickin' spacecraft can function. It's just mind-boggling. So these things were launched in 1977. So they're at their 45-year anniversaries and still functioning. Their power is declining, so several instruments have been turned off. The power of the radio signal that's coming back to the deep space network from these things is just ridiculously small, and they're quite far, and by some measures, some people would say beyond the solar system, but by other measures, not. So that's what our stumper is. What measure do you prefer to define the edge of the solar system?
I'll let Addie go first because I have strong feelings.
Oh man! Oh yeah! I feel like we've discussed your strong feelings before.
We have, but I've refined those strong feelings, I think. So,
okay, good. We've talked about this. Is it or isn't it out of the solar system? I think I know. I think I remember Jim's answer. I think that there are different definitions depending on what you're talking about.
Well, I'm talking to you, and you got to answer. I'm talking to you, and somebody says, "Where's the edge of the solar system?" You can. So you're going to say there's multiple edges.
I'm going to say it depends. I'm going to channel Attorney Tom, who is a YouTuber, and say it depends.
It depends.
Yes.
The edge of the solar system depends on.
Yes, I think it depends on there are different edges depending on which physical phenomena you're talking about. So if we're talking about the behavior of the plasma.
Well, that's why you got to pick one that you think is the definitive one.
I'm saying I don't have to pick. I'm saying I want an answer where I plop you down somewhere in space and I ask you in a spacecraft. You're on a mission of exploration or whatever.
Phew.
You've got a whole bunch of Netflix downloaded on your computer to while away the time because you got a lot of time to kill out there. I plop you down out there, and I want you to tell me.
And download speeds out there are going to be real slow, so make sure you preload that.
Are you in the solar system or outside the solar system? And so I want you to pick the line that you would use to answer that question.
Okay, I'm going to use the roughly heliopause boundary that we've been talking about off and on for Voyager.
Okay.
Then.
Okay.
I'm satisfied with that as a boundary in terms of a lot of the physical and phenomenological effects that we observe as being outside of the solar system.
Okay.
I do acknowledge that presents definition issues.
We'll hear Jim's strong feelings, I think, next.
No, that's wrong. That's the incorrect answer. The correct answer is the solar system edge is defined by the most distant object that is gravitationally bound to the sun.
So, does that?
I recognize that will depend. that will mean
So
you could have two stars of exactly the same size, and they'll have different size solar systems depending on the distribution of stuff and that particular thing, and what other stars are nearby and so forth. But I'm totally fine with that, because I don't know. I just like magnetic field stuff and tiny plasmas that I can't see. I don't give a crap. I want to know, where is the big thing that is orbiting the star? Where is the most distant big thing that's orbiting the star? That's the edge of the solar system.
So like if Oumuamua was coming into our solar system from somewhere else, where does it start to feel like can you define like where it starts to feel the gravitational effects and be pulled into our solar system? Does it have to be in orbit? Are you using an orbital definition?
I'm using an orbital definition.
okay, and
Classic.
you're not even you're using an orbital definition, but you're requiring that there actually is an object there.
Yeah. If there's no object.
So in other words,
So this is not a theoretical definition. This is a real world practical definition. I want the farthest object that currently is gravitationally bound to our sun.
But for this Stumper, then Josh is plopping you down anywhere. So
that's right.
You could be that gravitationally bound farthest object, and you could be setting the boundary of the solar system.
Damn, Skippy,
that's exactly right. That's right. So if I put you just beyond the most distant Oort cloud comet, and I said, "Are you in the solar system or not?" you would say, "I'm on the boundary line."
Yeah. If I'm orbiting that sun and staying around, then I am the edge.
Okay.
I wish I was the edge.
You're always on edge. Jim.
I don't like that. I don't like that definition. But you're obviously a gravity man, and Addie's is an electromagnetism woman. Both of those definitions.
Those are actually our alter egos. Gravity man.
We have a superhero group, and that's
yes. Josh is resonance man.
Resonance man.
These are all our
powers, but cool.
So Addie's size of the solar system breathes a little bit with the activity of the sun. Jim's size of the solar system depends a little bit on like where the sun is and its history. I mean, orbits out there change, and some things get stripped off. If we move into a crowded region of stars, some things are going to get mixed up and scattered around, and then by your definition, the solar system would perhaps shrink if we lost some of those more distant things. Okay, I find both of your answers very unsatisfying, but that makes it an
satisfying answer. That's the whole point to the Stumper, though.
I think you're right. I think you hit the nail on the head. Well, today we will work our way out from the Earth's atmosphere to the moon and to distant galaxies and supernova. But first, this episode of Walkabout the Galaxy is brought to you by leap seconds. With so much going on in the world, it's more important than ever to be able to count on the stable things in life, like the speed of light and the length of the day. Unfortunately, Mother Earth doesn't always cooperate, shifting its mass around like a twirling ice skater through atmospheric dynamics, evolution of the cryosphere due to climate change, and core mantle interactions, so that even the day doesn't line up with our clocks. That's when it's time to get a leap second added to your day so the sun and atomic clocks are in harmonious accord. If you didn't get enough leap the first time around, feel free to help yourself to leap seconds. Leap seconds. Tick different.
Tick different. Wow. There's think different, right? Or is it actually tick different?
Think different is a thing.
IBM is think different.
It's actually Apple is think different.
Oh, that's right.
Rolex.
That's just shown how much has changed since Apple came up with think different. They were the little tiny upstart outsider,
and not the
most valuable company on the planet.
So it
Jim
actually
says
is
Rolex.
tick different. Yeah, that's a good
guess.
Tick
different.
Omega.
Swatch. So you're on the right track. And Apple actually sued Swatch for trademark infringement for just the reason you point out. It's like, that sounds like think different. But that never really went anywhere. So
that's good. They're different words.
We're recording this on July 29th, 2022. And 1 month from today, do you know what's going to happen? Maybe?
Maybe Artemis.
Maybe the first launch of Artemis, which I really hope it happens on August 29th and not on the
Why?
two backup dates, September 2nd and September 5th, because we will be at DragonCon in Atlanta recording a special episode
Oh.
of Walkabout the Galaxy and other presentations there, and would miss seeing that launch from our
Well, if
backyards.
it happens August 29th, I might also miss it. So,
Okay, so you're hoping for a more
and
significant
I'm hoping for a
delay.
bigger slip. I mean, I'm
So,
not.
Okay,
I would love it to go,
so
but
what is happening on this launch? What is this
so
going?
this is the Artemis 1 mission,
Is
which
it
is
going to the
the
moon?
Space Launch System, which is the SLS, which is the big NASA slash actually Boeing and Northrop Grumman rocket that is going to the moon.
So what are they going to do at the moon? Is this
It's
just
an
like a proof of concept thing?
uncrewed, it's an uncrewed mission that's going to do a big loopy orbit, and it's not going to actually like touch the moon. It's going to do a little orbit thing around. It's going to drop off like 8
10,
little science 10
10
CubeSat
CubeSats.
sized satellites, some of which are going to be lunar orbital, some of which are deep space, so they'll be in a slightly different orbit. And it's going to test some maneuvers and some other things as the first demonstration mission of the rocket and the capsule in a lunar orbit.
And then and I was surprised to learn that the planned duration of that mission, because then the capsule, the Orion capsule, which won't have any people in it, but is the
Yes.
capsule that eventually will carry people back to the moon, will come back and splash down, and
Yes.
in sort of classic NASA throwback Apollo style, and
Slash now
that
SpaceX style.
that's true, and that reentry is at a higher speed than coming in from low Earth orbit, so it's another challenging test. But I was surprised to learn that the duration of that mission is planned to be between 39 and 42 days, depending on exactly when it launches. So much
Yeah.
longer than the Apollo missions.
Yeah, and it's longer than like I think a typical like the next phases and like more direct Artemis missions would be because they are just like testing out a lot more stuff,
Yeah.
I
So
think.
the next Artemis 2 would be a mission with people, but still sightseeing
Yes.
from orbit, not
Yes.
not touching the moon. And
Yes.
then it's the third mission that would put people on the surface.
Yes.
I'm going to say, I'm sure that many of our listeners know this, but how long does it take to get to the moon? I don't like.
It can
Depends how
you can
fast
do
you're
it like
going.
Apollo.
I mean,
Apollo was
obviously,
like
yes,
three
but
days.
one of the typical Apollo missions to the moon. How long did
A
that take?
typical lunar crewed mission, but Apollo used to take about 3 days.
Okay, 3 days.
Yeah.
Yep. Lots of good information in this little discussion here for our upcoming trivia, which we'll get to later.
Ooh.
Yeah.
There was an interesting announcement that's more technical, but about the SLS, the Space Launch System, the big rocket system, that NASA is probably going to like change the way they're contracting for those rockets, and they're going to do different types. So anyway, it's going to be a different type of service contract for like a set of Artemis missions. But I guess there are like up to 14 Artemis missions through 2036 that they could potentially contract, but they'll do them in batches at a time, and they'll contract with a new joint thing called Deep Space Venture, which is a combination of Northrop Grumman and Boeing for the different phases, parts that they build of the rocket. Anyway, it's NASA's trying to do these contracting things differently to make it more commercial, and so that these companies could potentially like sell this rocket to other folks as well.
Well, there's certainly still some uncertainty about what the long-term prospects for the Artemis program are in terms of really going back to the moon the right way this time, meaning
Yes.
In a coordinated, permanent presence. And it doesn't mean necessarily you got to have people there every day of the year, but that
No. But you build up infrastructure.
you're building up infrastructure as you go, instead of like, I went here, I dropped some stuff, and that's it.
Yeah.
So
Yeah.
that's still, I
Sustained.
think there's a lot of uncertainty around that, because that depends on the U.S. government and partner organizations, if we partner up with other governments making long-term funding commitments to it.
By the
Yeah,
way,
and Orion just gets us into orbit and then like around, but there's actually a different lander that is built by other companies that
Right.
must provide the ride to the moon and up from the moon. So
I'm very concerned. By the way, you've told me something here that makes me very concerned about the entire Artemis thing. The whole thing is going to fail because I have a boat. It's a like a 35-year-old aluminum bass boat, and it's Grumman is who made it, and it leaks like a sieve.
Oh,
I think that's the
jeez.
same company. I think so. Artemis, good luck.
Let
I
me
think
ask you why you have a boat that leaks like a sieve for 35 years.
Well, I haven't had it for 35 years. It's mostly because I don't know how to maintain it properly, probably. But
Do you know how to haul it to the dump?
I desperately need a new boat. Josh, I'll be expecting that $30,000 soon.
Okay. Well, you know how Artemis 1 gets to the moon? It launches and it goes through the atmosphere
that's true.
of the Earth.
Oh, I was going to do a couple of other space newsy things real quick before we get to that. That was a really good
Okay.
transition, though.
I thought I was so happy with my segue, but go ahead.
Sorry. So I was just going to say that there's Blue has announced that their next crewed flight, their next space tourist flight will be the beginning of like, I don't know, 5 days from now, August 4th or something. So they're flying
Okay.
more passengers, more paying people to go. And today or yesterday, Maston Space Systems, who is building a lunar lander and who is contracted to supply some of the science payloads that are supposed to go to the moon from NASA, declared bankruptcy. So that's problematic. Like
Oh
it could be that they're
no.
declaring bankruptcy to like clear out some stuff and then do a little bit of restructuring and still be able to do some contracts, but it seems like maybe that's not the case.
That's bad news.
Yeah.
Sorry to hear that.
I mean, yeah. So it's like it's not surprising that some of these early companies, right, aren't going to fully make it, and NASA, that's why NASA funds a bunch of different companies,
Right.
but it's still a bummer when you're expecting a ride on it. So anyway,
Well,
but you know
way
what
to
is
bring the
launching?
podcast down, Addie.
You know
Yeah.
what is launching? So many rockets, especially from here in Florida.
So many rockets, and you're going to have, speaking of Blue Origin, I know you've got a payload coming up on a future Blue Origin flight as well. Not the one with peoples on board, but
No, it got pushed
so
back
we'll
because
be
of the one with people.
the stoned peoples.
I
So
know.
well, but we'll be looking forward to hearing about that. And you know where Blue Origin's suborbital rocket goes? It goes into the
Where does it go?
mesosphere.
It
Into the
does.
mesosphere. So I
Where's the
pulled a
mesosphere,
second
Josh?
amazing. The mesosphere is where mesospheric clouds sometimes appear.
Interesting.
So I
You sure
pulled
it's not
another
the
amazing
mesosphere, huh?
segue.
What
I
was that,
am
Jim?
sure it's not the mesosphere. Me so
Meso.
sure it is not the mesosphere.
Meso. Meso.
Meso. It's like
It's
Z
not the
sound.
mesosphere. Oh my gosh. Jim.
I'm just saying. Okay.
Anyway, there is a new paper from some of my former colleagues from Colorado, are among the
Mm-hmm.
co-authors of this paper, Cora Randall and Dave Siskind, about mesospheric clouds. These are
Yeah.
also sometimes called noctilucent clouds because
I
they're
love that
super,
word.
super, super high in the Earth's atmosphere. So high that noctilucent meaning nighttime glowing, I guess,
Mm-hmm.
for a sort of approximate translation, because the sun has set from our vantage point here on the Earth, but 50 miles up in the mesosphere, these cloud ice particles can be illuminated by the sun, and so you would see these glowing, eerie noctilucent clouds.
Yeah. And and like you mentioned, these have often been observed just visually from ground-based observers, and they're often at more northern latitudes where people see them, and a lot of folks who study noctilucent clouds study them from like Scandinavian regions and Alaska and stuff like that. But there's also been some satellites that were put into orbit a while back now, to look at things like Noctilucent clouds. So to look at atmospheric effects, and atmospheric variability, including this instrument from the called the Cloud Imaging and Particle Size Instrument on the AIM Aeronomy of Ice in the Mesosphere satellite, which is a fun satellite that's been in orbit since like 2006 or 7. Yeah, 2007. So a long time. I think I remember when it launched. I think I was at Colorado then.
You were.
I was. And they have been studying the variability of these noctilucent clouds. So there's a lot of questions of how they form. And so like clouds form because they get seeded on dust particles and things like that in the atmosphere. And so you can look for variability in these clouds to tell you some interesting things about atmospheric dynamics and where there's particulates, and how those vary over time. And they found in this new recent paper they published, they found a correlation between noctilucent clouds and rocket launches. So when we launch rockets, they produce particles, right? So their propellants are producing particles that then are distributed in the atmosphere. And specifically, they found correlation between launches that occurred in the late night, early morning hours. So like 11 p.m. to 10 a.m. local time. So they were looking at launches from like Vandenberg, specifically Vandenberg Air Force Base out in California, which typically are a lot of times polar launches. And so these launches happen, and then they did some models of where the winds go and where the particles would go, and they see a correlation with some of the increase in noctilucent cloud observations with launches from Vandenberg.
Interesting. Okay, so all right, so there's a lot to process there. So
it's a long paper.
The clouds are basically at those altitudes. They're water ice, tiny water ice particles those water molecules have to have a condensation nucleus, or I'm not, a seed, or I can't remember the technical term used, but some solid particle has to exist for the water ice to then glom onto and condense and grow into making this little cloud particle. So it's basically rocket exhaust ash in some sense that is acting as those seed particles.
Or are these like solid rocket? Like the space shuttle would use hydrogen and oxygen and then wouldn't leave little solid particles behind because it's just water.
It's water vapor.
These are solid rockets that are burning like rocket fuel. Whatever.
Some of the rocket fuel does produce water. Some produces like hydrazine produces some nasty stuff, and a lot of them produce just like some little other particles. I don't actually know. I can't think off the top of my head right now what all is produced.
The solid motors definitely do produce, there's aluminum in there and other elements that could produce little solid nucleation site, I think is the term I was looking for. So, and then when you mentioned polar, so that's a polar orbit. So like the Vandenberg launches are like going north or south. It looks like they're mostly going north on a highly inclined orbit. So it's not the exhaust that we see when we see the launch from the ground at the very low altitude. It's whatever is burning when the rocket is high up, which could then be like second stage rocket exhaust or things like that.
They do modeling from what is moving from when it's still at the lower latitudes, so more from the launch latitude. So I think it is still like the early phases.
Well, it can move in latitude north, but it's probably like still, I mean, I don't know. It could, of course, be still the first stage, but we see a huge cloud of fire and smoke at the launch pad. The mesosphere is much higher, so this is exhaust that's produced much higher. Mostly what rockets do is they go up and they make a sharp.
It's produced higher. it's stuff that like is advected and transported due to thermal gradients and
Oh,
upper
wow.
atmospheric
Okay.
winds and stuff like that.
Okay.
So I don't know if it has, so I don't know if it's as much that like, I couldn't tell from my, I need to reread the paper probably, but I couldn't tell if it was just that like because they're more polar launches, they are helping transport it there, or it just happens to be like at this launch location and the wind directions and transport processes are what are moving things more northwards,
Okay.
Noctilucent clouds.
Okay. Right. And then presumably the environmental conditions in the atmosphere up there in the polar regions are more conducive to producing these clouds. So yeah, it's
Mhm.
funny, the clouds called noctilucent clouds based on Earth surface observations and polar mesospheric clouds, as you mentioned, when we have the more satellite observations and see a more global view and see that they tend to be more concentrated around the polar regions. I've never seen
Yeah,
one, but that would be cool.
I haven't
Um,
seen those or aurora.
yeah.
And I
Well,
would say so when they started this analysis, they were looking for like annual variations and any sort of natural variations, and they like don't line up with any multi-year trends or solar cycle or anything like that. And then they were like, oh wait, let's look at these rocket launches, because some previous authors had suggested, like back from shuttle days, you mentioned, Jim,
that
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 there
could be
might be
seeding.
some tie-ins and that there might be continue to be more.
Cool. Yeah. So
It's kind of fun.
horizontal winds from a meteorological analysis system between 90 and 95 kilometers altitudes, that's 50, 60 miles up, suggests that an exhaust from a launch in California on June 12th, 2019 is responsible for a burst of clouds observed by this satellite uh, and from the ground on June 17th and 18th over Western Europe. So pretty cool.
Yeah.
Is there anything or so rocket launches are maybe seeding these interesting looking clouds? Are the clouds of any consequence aside from being a interesting phenomena? These are not climatologically impactful events, to my understanding.
Yeah, I don't think so. I mean, I think that they're good because they're tracers of certain atmospheric processes, but I don't think I've ever seen anything that says noctilucent clouds are like telling us of any bad things happening in our system.
Yeah. Well, I'm going to use that as our segue to our next topic of the moon, which is, I'm sorry, what I meant to say is I'm going to use our trivia to take us to our next
I was like, that wasn't a good
topic
segue, Josh.
of the moon. The trivia is the segue. The trivia is the segue.
Okay.
We talked a little bit before about the duration of Apollo missions and the duration of the first Artemis mission, which will be more than a month long. So I have a series of duration-related spaceflight trivia questions and one just sort of bonus, other random curious bit of spaceflight trivia. What was the duration of the longest humaned Apollo lunar mission? What was the duration of the longest space shuttle mission? What is the longest single stay in space for a human? And what is the most cumulative time spent in space by any human?
Oh, I should know all of these.
Really? I don't think you
Uh,
should know all of these.
I should know all of these.
I think
Being
you.
me, I should know all of these.
I think you should get reasonably close, and certainly closer than a random person plucked out of the phone book. But I
Yeah.
guess phone books don't exist anymore. So anyway, we'll come back to those after our other two topics. So the first one is the moon. Take us back to the moon. Uh, there's there are these cool features on the moon that the first time I saw a picture of one of these, I'm like, that can't be real.
They're so fun. I remember when we
So
first started discovering them, and you're like,
what are
what?
they?
First of all, it turns out they're maybe not that cool. Oh,
Oh,
they
nice.
may be
Yes.
warm. So there are
So
these things that are called pits on the moon. So the moon has some pits. The moon's the pits.
so they look very, very different than craters. These look like
Yes.
somebody went to the moon with a giant drill
Yeah.
and drilled a hole straight down 10 or
Yeah,
20 or
somebody's
30
just been doing
meters or
sampling at
more.
different places on the moon.
Yeah.
Um, so pits tend to be, oh, that's a good question. I
They're
forget how
they're
big they
sort
are
of
across.
like they're like 10 meters across ish,
Yeah.
10,
They
20,
have diameters
30
from
meters
15 to
across,
150 meters.
and comparable depths. So depths
Yeah.
up to 150 meters. Oh no, sorry, I was looking at the diameter. But they're also those sorts of depths. And I believe the explanation for them is that they're sort of ground collapse into lava tubes underneath the
Hmm.
surface.
Yeah. So
So
we see this on Earth, where in places like Hawaii and other places where we have more active volcan, Hawaii.
Oh, okay. I thought
I
you said
say it
go ahead. Hawaii. Gotcha.
where there's more active volcanism because so basically like when you have lava flowing underground, it'll flow and create a lava tube. But then a lot of times it like sort of creates a hollow structure once the lava has flowed through. If it continues, if it clears out, you're just left with that hollow tube, and you can actually like explore lava tubes in Hawaii. That's super fun. But sometimes then you'll have, if there's a weak spot on top, you'll have it collapse in, and that's how you can create these pits. And so we have them here on Earth, and they think that's most of what these are on the lunar surface. And some of them you can see some like rills that seem to be where there's lava tubes underneath the surface on the moon.
So these things tend to be circular?
Yes.
yes,
Like they aren't all perfect circles, but a lot of them are very, very circular. Yeah.
yeah, and they look really bizarre. They look very artificial, um,
Hmm. I
because
think
we're
it was
used
the
to seeing these
Japanese
sort of
spacecraft.
bowl-shaped craters. It was
Yeah. That first started
the
returning pictures of these. Selene.
Selene, yes, in 2009. So relatively recent discovery that these things are there. And I guess this new
Mhm.
work has to do with sort of potential uh, future human exploration of going for a stroll through
And
these pits.
habitation. Yeah, so
Yeah,
one of the big problems if we try to live on the moon or most other planetary surfaces in the solar system is that there's not an atmosphere and there's not good like radiation protection. So ever since these pits were discovered, they've been thought of as interesting potential for pre-existing structures where you could build habitats that are under the ground and provide natural shielding and protection. Um, but this new, and so they've been characterized a lot in terms of like how deep we think they are, and if they have like spatial regions around them um, where you could have your like long tube of housing or something. Um, but there's a new paper that looks at the thermal environment. So this is using the Diviner instrument, which is on the Lunar Reconnaissance Orbiter. And Diviner looks at thermal signatures on the lunar surface. And so they did a bunch of modeling to sort of see what temperatures the floors of these caves and the floors of the pits might be at over time. And it turns out that they actually are like fairly stable temperatures, and they're fairly warm. I mean, uh,
Relatively, right? I mean, they can't be actually warm, right?
well, they have some.
they
They
can
had
be.
one, so they did it for one crater, and it was that it was 17 C or about 63 degrees Fahrenheit over the course of um, the day, except when the sun was shining directly down in.
Right. If
Huh.
you're, yeah, it can be very
Yeah,
hot
That's comfy.
at noon,
yeah.
with the sun overhead if you're one of these holes because the energy is coming in and most of the energy doesn't get out. And so then you can get very high temperatures. But if you move away from that opening, so you're not at that hot spot where the main source of the energy is, you're insulated from the
Hmm.
normal day-night temperature fluctuations by the mass overhead. You've got then a time averaged energy source into that hole from the sun that gives you an average temperature, which, because it's the same distance from the sun as the Earth, works out to be comparable to the average Earth temperature. The details, of course, are going to depend on obviously the Earth. There's atmospheric trapping of heat and things like that, but uh, the moon, on average, you've got the same solar input, and if you can get rid of the fact that on the surface of the moon,
That
at
it's
the nighttime, you've got 2 weeks of radiation just flying off into space and dumping all that heat away. You get rid of that
yeah,
by trapping everything underground. You have an average temperature of 290 Kelvin, which is
Nice.
like
lovely.
I would love it if it were 290 Kelvin outside right now.
Yeah, I
Could,
know, right?
Yeah. To be clear, though,
Yeah,
this is something that confuses my students sometimes. Like, be careful about what you're talking about the temperature of. Obviously, there's not air there, so usually when we talk on Earth, talking about temperatures of things, we're talking about the temperature of the ambient atmosphere. Here, it's like the
yeah,
right.
temperature of the surrounding rock. Which, of course, if you
yes,
pumped an atmosphere in there, then it would kind of equilibrate and you'd be comfy. But
yeah. That's a good
don't just
point.
stand around in those tubes with your shirt off because you are going to die.
Yes,
Well, you'll die,
but
but you'll die
you'll
because
be
you'll.
thermally
Not die of
comfortable.
cold. You'll die because of.
Yeah,
That's right. You'll die because that's right. You'll die because you're suffocating, but not because you're boiling or freezing. Because
yes,
you'll be in a thermal environment. The thermal radiation coming to you will be radiating from a surface of about
yeah.
300 Kelvin.
Yeah, it's
Um,
pretty crazy because, like, in these areas on the moon, which are like fairly equatorial, right? The one they were looking at, it's like down to 100 Kelvin at night. It's very, very cold, and like 400 Kelvin or 350 Kelvin or something during the day. So, like, there's these huge swings, and it's really, really cold and really hot. But there's some sort of nice equilibrium that might happen um,
yeah,
in
63
the rock.
Fahrenheit
That sounds
with just a
lovely
little
right
bit of
now.
variation. So so you get two good things if you want to set up a base in one of these pits. You get a nice, constant, reliable thermal environment, and you get
Yeah,
protection from solar radiation, which is a big deal.
yeah.
You don't have a good view.
No,
Um, you'd want to make sure that maybe put some reinforcement in because the pit exists because something collapsed at some point to give you access into that
sure.
lava tube. But yeah, so that's pretty cool, or not so cool, depending on your point of reference. All
For
right,
Floridian, 63 is pretty cool, I guess.
it is pretty cool for us here in
But it
Florida.
sounds
Um,
lovely.
and and those temperature measurements are made, as mentioned, by the Diviner spacecraft, which is looking in the infrared part of the spectrum, the same part of the spectrum that
Hmm.
the James Webb Space Telescope uses
Oh, wow.
for very different
Nice.
purposes.
Hmm.
These infrared measurements measure the temperature of things producing that infrared radiation, and the James Webb Space Telescope uses infrared to see uh, through uh, dust in our own
Space
galaxy, but
and
also
time.
to see very, very distant objects. Jim
Yes.
can explain why and how. I'm
Yeah.
on a segue
So
roll today.
And
yeah.
this is part of one of our new segments, which is going to be JWST features almost every episode
Right.
now.
Right.
What's new?
Right. I mean,
What's new
everybody
with
was so
JWST?
floored by those first, 4 or 5 images or data dumps from JWST. But now there's going to be like an infinite number of those going forward,
Yeah.
and everything is like brand new because it's just like this
Yeah.
box of candies that would just so yeah, just about on every podcast from now on, we're going to be saying something about something that JWST has illuminated. Um, but even in just remember the very first image that got released, which was that deep field at the 12.5 hour
Mm,
exposure, I mean, that's just like a gold mine of stuff, and people have been spending a lot of time looking at that and seeing all kinds of fun stuff in that, and so I just wanted to highlight some of the cool stuff. I remember. So one of the cool things, of course, is that you're seeing galaxies that are ridiculously far away, and obviously one of the fun things we always do is like, what's the most distant galaxy we've ever seen? And we've been talking about that for years and years and years. And I remember, I mean, just like less than a decade ago, getting super excited about a thing at z=8. And I'll explain what that means in just a second. Um, the way we kind of a proxy for how far away galaxies are is what their redshift is, right? Because the further away you look, the farther back in time you're looking, and the further back in time you're looking, the more space has expanded since the light left that thing. And so in cosmology, we use this thing, the redshift, to determine kind of how far away a galaxy is. So, for example, a thing with a redshift of 1 Z equals 1. Z is the, for whatever reason, we use the letter Z to indicate redshift. Z equals 1 means that the light has doubled in its wavelength. So space has stretched out. So now it's twice as big now as it was when that galaxy let out its light. And that
just
tells you. Go ahead.
For point of reference, the human spectral range that we can detect with our eyes is less than a factor of 2, or barely a factor of 2. We see light, the shortest wavelength light we see is about 0.4 microns, and the longest light we can detect is about 0.7 microns. So at the bluest light that the human eye could detect would be shifted into an invisibly red color if it were at a redshift of 1.
Right. And so almost everything you see in astronomy, almost everything we ever talk about is at a redshift of much less than 1. All of our local environment we don't even use redshift. It's when you're talking about things that are millions of light years away or something like that, that's not a redshift of 1. That's much less than that. That's our local environment. But when you want to talk about things that are crazy far away, you can start talking about things in terms of their redshift. And so a Z equals 1 object is ridiculously far away. Therefore, you're seeing it as it was when the universe was quite young.
Put a number on ridiculously for me.
Well, you're talking about billions of light years. So actually, I should know the answer to what Z equals 1 is in terms of light years, but it's probably something like 10 billion light years, that kind of distance. Maybe you're looking it up now and you can correct me.
I am.
If it's
10.147 billion light years.
I was so ridiculously close.
You were so
genius.
Close.
You're a genius.
So anyway, it's far away. Hubble, of course, could do the same kinds of things that JWST does, but just not as well. And so the most distant objects we'd seen through the Hubble era were something like Z equals 8 or something. I mean, that means that
that's pretty good.
That's pretty crazy good. Now
I have to just jump in. Z equals 8 does not mean 80 billion light years away, though.
No.
Even though Z equals 1 is 10 billion light years away.
Right. This gets weird and complicated. It's not a linear thing. 8 times the Z is not 8 times as far away. But it does mean it is a lot further away and a lot closer to the beginning of the universe. And so I don't know what Z equals 8. Z equals 8 is something like 500 million years after the Big Bang. Crazy thing like that. And that's pretty close to the beginning, by the way, of when we think galaxies would have first formed. So we're very excited to see galaxies that early because that's illuminating the dawn of galaxies, right? When galaxies first started to glom together. JWST has now seen things that are, and all of this is fairly preliminary because this is all brand new information, but 15, 16, 20, I've even heard that people think that there's detectable galaxies at Z equals 20. These are things that are maybe 200 or 250 million years after the Big Bang, before we even thought that there might even be galaxies. So that's one of the really cool things that JWST is doing, is it's changing our understanding of when galaxies first formed and how big they were when they first formed and what their shapes were. It's so freaking good that we can even determine what the shapes of some of these galaxies are. Not in any, grand detail, but is this a spiral galaxy or an irregular galaxy? You can determine that with it's ludicrous. It's ludicrous. So
and some of these galaxies are more complex than we might, because you might think early galaxies are just going to be not as complex because they didn't have as much. I just lost all my words, but anyway, they're more complex than we would have expected too.
Yeah. There's more big spiral disk galaxies than we thought, which means that we have to kind of reevaluate our understanding of how galaxies evolve in the universe.
It's reminding me a lot of go ahead, Josh.
A redshift of 10, the universe was about 500 million years old. About 480 billion years old, 480 million years old, sorry. Depends a little bit on some of the other parameters you put in there. A redshift of 20, the universe was 180 million years old.
Yeah, I mean that's borderline before we thought galaxies should exist, and so if we're seeing them, So that basically means JWST is seeing the first galaxies in the universe. I mean, that's it.
Pretty crazy.
That's your, and of course that was one of the things that prompted the development of the JWST was we want to see the first
earliest
galaxy.
universe. Yeah.
And the fact is we're seeing it in like the first data dumps that we have. And it's just like a 12.5-hour exposure. I mean, that sounds like a long exposure, of course, if you're doing it. But there are plans for much deeper exposures than that. And so we're going to get, not necessarily see galaxies that are that much further away because they probably don't exist, but you're going to get more detail on those galaxies that you see. And it's a gold mine if you're interested in galactic astronomy.
Are we allowed to say data dump?
I think so.
Okay.
Because he was very lifelike. He probably did that.
I was surprised that Jim didn't say anything about the warm pits on the moon.
I know. I'm maturing. Now that I have a child, I'm much more mature.
Unlikely. I call shenanigans.
All right. Let's see what you think about. Let's see how close Addie gets. Jim got remarkably close on his z=1 distance.
Yeah.
Number he should know, and it turns out he did know it. What is the duration of the longest Apollo lunar mission with peoples?
Should I guess first because I have much less idea than Addie on all
of
these?
Go ahead.
Sure.
14 days.
It's not 14? A bad guess. Yeah. I am going to guess 17 days.
Jim wins it, Addie.
Yeah, I know.
12 days, 13 hours and change. 12 and a half days.
Yep.
What was the duration of the longest space shuttle mission?
43 days.
Does this include like shuttle going to ISS?
Yeah.
Oh. What did you say, Jim?
43 days.
Jim said 43 days.
This is even more arbitrary than my guess on Apollo.
Yeah. I'm going to go with 37 days.
Addie gets it, but I'm disappointed with how far off you both are. 17 and a half days. Yeah.
Really?
Yeah.
Oh.
Yeah. And it was only that long because its landing kept getting delayed by weather conditions at the landing site.
I thought there was at least one that was closer to like 3 or 4 weeks, but
yeah. What's the duration of the longest single stay in space for a human?
1.03 years.
633 days.
I think Jim wins the 438 days by Valery Polyakov on the Mir space station from January 94 to March 95. And then what's the most cumulative time spent in space by any one person?
That plus 50 days.
That plus 50. I'm going to truncate all these long, thoughtful silences in the editing. So for our listeners who think, boy, these guys are just popping their answers off really quickly, just be aware that I've edited out minutes of dead air of them pondering the answers to these trivia. Okay. Jim says 50 days more. So Jim says 488 days.
I'm going to say 633 days again.
Addie gets it. It's 879.
Wow.
879 days, multiple missions, of course.
Yeah.
By Gennady Padalka, probably mispronouncing that. And then this is not a duration question, but it's probably more interesting than the other trivia questions that I should have just stuck with this one. What was the nationality of the first non-American, non-Soviet citizen to go to space?
Pakistani.
Interesting, bold choice.
Thank you.
I'm going to go with, I don't know, French.
Addie's closer on this one. Czechoslovakian. Czechoslovakia
Oh.
at the time, Czech at the current time, and the person is Vladimir Remek. In March of 1978 on a mission called Intercosmos, is also considered to be the first European in space. Well, while it may have felt like either the longest space mission ever or waiting for the Astroquarks to answer a trivia question, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give us the universe. We'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel. Our second and long promised music video is in production. Please be patient. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG. Our theme music was composed by Richard Jurisic. Production assistance is provided by Logan Basinger. Thanks to our listeners in Bay City, Michigan, and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
And I'm Jim Cooney.
We're the Astroquarks, signing off until the next episode of Walkabout the Galaxy.